Okay, so the next topic that we want to discuss is what we call the linear transformations. It's not a transformation because there are so many maps. You can define linear transformation in whatever way you want. So it's basically a function that takes values from some Rn and maps it to some Rm. So you take a vector from Rn and you apply some sort of transformations and you get a vector in Rn. So you take a vector, you apply a transformation, you get a vector in Rm.
And are the dimension or
Dimensions. For example, you take a vector in 3 dimensions, you get a vector in 2 dimensions. You get a vector in 2 dimensions, you input a vector of 2 dimensions, you get a vector in 3 dimensions, and so on. So this is a very beautiful idea. We'll be looking at this geometrically, what does it mean, by looking at so many examples. But basically, this transformation must satisfy certain properties. It is not the usual transformation. And the thing is that these n and m can be equal as well. Now you take a vector in 2 dimensions and you get a vector in 2 dimensions. Like you get a vector in 2 dimensions and this is the vector and you rotate it. This is also linear transformation. So you rotate a vector in 2 dimensions, you always get a vector in 2 dimensions. So when these n and m are equal, it means we are in the same space. We are picking a vector from R2 and we are sending that one into R2 again. And we are taking a vector in R3, we are sending it to some vector in R3, some other vector in R3. Now, when these n and m are equal, we call this linear transformation to be an operator. You can see the things are related. Linear transformation, you pick a vector from Rn and you send this vector to some other space Rn. But if you are playing with the same space, you call it operator. It means you pick the vector from same space and you send the vector in the same space. But maybe this vector will remain same if your linear transformation is identity operator. And if the operator is, let's say, a rotation operator, then your vectors is being rotated and so on. And sometimes there is a function when you take vector in Rn, it gives you output in your field. So you pick a vector and your output is a number. We call it a functional. So what does the functional do? You pick a vector and you send it to a number. Number can be real or complex. Operator Rn to Rn and linear transformation from Rn to Rn. So we'll be discussing these things in detail when we study functional, and basically functional analysis is a study of functionals. So what is a functional? You pick a vector and you send it to a number. What is the example? Example is the norm of a vector. You take a vector, your output is a number. The angle between 2 vectors. But angle between 2 vectors is not a functional. Because in that one you need 2 vectors. In this one I need 1 vector. So that can be a functional of another type. And you can define that functional and you say that okay, you take 2 vectors. And whenever you take 2 vectors, you write some sort of cross product. It means you are picking 1 vector from here, you are picking 1 vector from here, and you are finding angle between them, and angle will be angle can be r, can be from 0 to 2 pi, depends. Okay, so we are only concerned about linear transformations. So this is a function that satisfies 2 properties. One is that you take 2 vectors and then apply this operator or transformation. It is same as operate T on V, T on W, then at. The answer will remain
Distributed property we can say.
yes, it is distributed. Not distributed. It is linearity.
Linear.
It is linearity. It is called linearity. And the another one is you scale a vector and then apply linear transformation. It is same as apply linear transformation and then scale. So if these two properties are satisfied by that operator, we call that to be a linear transformation. And we can write these things compactly as well. It means these two things can be written in one way as well. That is C1V, C2W is same as C1, C2 and T operated on W. Here both of these operations are applied together. There is a scalar multiplication as well as addition. So either you write these two things, these are the properties for linear operator or linear transformation, or you can compactly write only one thing. The things are same, no difference. We will be doing examples as well. Okay, so example number one is you take a matrix from this space, and what is this? This is a space of n cross n matrices, and you pick one matrix out of that space, and you define your linear transformation from Rn to, let's say, Rn. And how do you define it? One thing is that when you define a map, you always say that where does your map start and where does it end. So what is the start of your map? You pick an n-dimensional vector and you send it to some sort of n-dimensional vector. And then what is the formula that relates Rn to Rn?
Function.
Yes. Whenever you define function, okay, your function goes from R to R plus. Then you define, okay, what is the formula? So you say f of x is equal to x square. So these are two ingredients to define a map. Otherwise your map is not defined properly. Okay, and sometimes you say, okay, you take x and you send it to x square. This is same as saying this thing, f of x is equal to, whether you say this or this, no problem. Okay, and how can you check that your map is well defined? Well defined. You pick one element from here, the answer must lie in R plus. If it lies in R plus, you say that your map is well defined, otherwise it is not well defined. So how do I define? I take a vector in Rn, I operate D, it is same as, so what is this? Multiplying V with matrix A. So I define this linear transformation by multiplication of matrix A. And this is linear transformation. You take a vector V, V is in Rn, and you multiply with the matrix A. What is the order of A? M by N.
So n.
So what is the order of A?
Mn.
Mn. What is the order of V?
N. Yes.
N by 1.
So, yeah.
N rows, 1 column.
It's possible.
So what is the total order of this? Does it belong to Rn? Obviously. Is it linear? How to check? So you take a vector, you multiply with a matrix. So multiplication by a matrix is a linear transformation. How to check?
Common bedroom.
Yes. So you have to find that you have B plus W. How do you do this? A multiplied by B plus W. Because T means multiplication by A. And you can, multiplication by a matrix is distributive, we know very well. So you can say this is AB plus AW. What is AB? So this is equal to, hence it is linear. So this is by definition, we can check. Similarly, we can check the scalar multiplication as well. So multiplication by a matrix A is a linear transformation, and we will see different examples of this multiplication later on. What is an example? So let us discuss an example. You take a vector in R2, let's say this is AB, and I am going to project it down to x-axis. So what is this vector? A0. So basically this is not A0, this is only A. If I consider one-dimensional space, so I call it only A, let's say. So you have a two-dimensional vector and you are transforming it to one-dimensional. It means this is a linear transformation from R2 to R1. And you can also define a matrix for this linear transformation, and the matrix would be this one. When you multiply these two, what's answer? It's A0. A0 or only A. The second component will always be 0. If the second component is always 0, it means you are on a real line. So if you are on a real line, it means you are at one dimension. So you can say that the linear transformation is the projection geometrically, but you can assign a matrix to this linear transformation as well. So sometimes your linear transformations can also be represented by some matrices. So you are going to connect the idea of linear transformation to matrices. And we will see so many examples of this matrix. Projection on x-axis, projection on y-axis, rotation, reflection, and so on. There are lots of examples.
So, well, I'm not sure either my question is connected with your. If a vector having I have not been to the dimension, okay, but I have been to either I rotate left or right, the length will be remain same. So what if I change the values like A, B, and A0? So what do you think that the length will be remain same?
No. It's length will be different. What we are doing, we are projecting vector down on some space.
Okay, vector तार मिले अनुसार माँ जरूर लगेगा vector तो जाएगा vector से मिला ठीक है two one dimension में मिले तो ठीक है पर उन्हें जो properties अंदर physical property वो इसमें क्या होगा
then
length था उन्हें जो
so then a linear transformation property can define you only define okay these are two conditions to be satisfied.
सर left and right side भी बराबर है ना इतने सुधा उधर linearity थी हुई जो property है मिसाल physical property में length था length मुझे ख्याल में vary कर दी ना
it varies for example
चले ना भाई left right बराबर है क्या उधार तो length भी vary ना जो ठग ना
length very thin because linear transformation is only following certain properties 1 and 2. If those are satisfied, that's a linear transformation. We are not concerned about the preservation of length. We are not concerned about any other thing. We are only preserving a particular quantity. For example, if you take this vector in R2 and you take this vector in R2, you project these two vectors down, you will exactly get the same vector, let's say. Now the length of this one
it's not equal. Both
is
are
not same as this one.
both are different.
But when you find the linear transformation, you get this vector. It means we say that this linear transformation is not what we call 1 1 or what we say it. For example, you take a vector v1 and you get a vector v2, and then you get another vector v1 prime. You also get a vector v2. It means two different vectors are there, but you are getting the same vector. It means these certain types of linear transformations are not 1 1.
Yeah.
You take different vectors, but your answer is same. It means this is not
No.
1 1. So maybe this preservation of lengths or another idea is satisfied by what we call bijective transformations. We'll be looking at that later on. Okay, so another example is number 2. T from R2 to R2, and you define this. Is this a two-dimensional vector? You get a two-dimensional vector, and your output would be two-dimensional. It means I am giving a comma in between, and your output would be of this form. It means if I say you what is the transformation of 1 1, how do you transform 1 1? You will put 1 1 here. 1 minus 1, 0, and 1 plus 1, 2. So your transformation of a vector 1 1 is going to be 0 2. This is an example. My question is this linear or not? So you can check whether this is linear or not. But I am going to tell you how can you check readily. So T from, let's say R2 to R2, and I define T in this way. I define T as dx square plus y so this is linear and this is not linear. Can you tell me why? This is a linear transformation, you can check, but readily the powers of your these variables. So what is a vector? Component x, component y. Everywhere the power of that component is going to be 1, and here the power is 2. Here the power is 0. So it should be 1 everywhere. So because of these two things, even if this is involved, then again it's not going to be linear. If this is involved. So the powers of your components should be 1, then it's a linear transformation, otherwise it isn't. So this is a small check. Otherwise we can satisfy both properties, but it's very lengthy to do it.
But if I'm writing x plus 4 there,
Not linear. You can check it and you can discuss with me, okay, whether what happens.
So sir, whenever we are giving a linear transformation, so that must be t of x comma y.
This is operator T,
Okay.
y x comma y,
We have
because you are taking a vector from R2.
Or-
If this is R3, that would be x comma y comma z.
See,
If
and
this is R4, then there would be 4 things.
four things and power must be 1. On each-
No. Here you will only take the vector that you assign. Here you will take x, y, z and a, b, c, whatever. But here you can write some crazy things. Because you take x and y and you plug in this formula. Now here you can get different things, but here it will only be x, y, z or whatever.
so if our function is in modulus form, x minus y mod form, then does it be linear or not?
I think it will be linear. It will be linear. But you should check. I'm not sure about this. You should check about the absolute value. The absolute value I think follows linearity. Absolute value function itself follows linearity. And when you take this type of function, I think this will not follow linearity itself. You can check this thing. Okay, so these are some examples to check whether these are linear or not. So, what is something good about linear transformation? So you have a vector v. You can write your vector in this way. You know very well. v1, e1, v2, e2, up to vn, en. What are these e1 up to en? These are orthonormal bases. Orthonormal bases means EI dot EJ is either 1 or 0. 1 if I is equal to J and I is not equal to J. It means E1 dotted with E1 will give you 1. E1 dotted with E2 will give you 0. This is what we call the property for orthonormal basis. You can write this compactly as it is same as delta Ij. What is delta Ij? It's a Kronecker delta. It gives you value 1 and I and j are equal. It gives you value 0 when they are different. So this is the property for that. Now I apply a linear transformation on this vector v. Then what happens? Then what happens exactly? Now the good thing is that I am interested in finding a matrix of linear transformation. I wrote some linear transformations x minus y, x plus y on the previous board you saw. Now I have that thing, but that thing is not good to study. So I am converting that thing into a matrix. I have a linear transformation, I am converting that thing into a matrix. And I can do with the help of this. You know very well, if I pick any vector in Rn, since we are only concerned about Rn, we are not concerned about any space, we can always write that vector into this form, into the linear combination of orthonormal bases. I am applying linear transformation. It means I will apply T on this whole thing. But you know very well T is linear. T is linear. And what is V1? It's a constant. So it is same as this. Because linear transformation is always applied on vectors, not scalars. Then up to what is this? Vn. Are you okay up to here? Okay. Now, can I write this thing into this way? What is V1, V2 up to Vn? What are these?
Component of vectors.
They are component of your vectors V. It means you can say that this linear combination is same as multiplying a matrix with this column matrix V1, V2 up to. What is this? This is a vector, but in column form. Now T of E1 is going to be the first column of your matrix, and T of E2 would be the second column, and so on up to. And this is what we call the standard matrix of linear transformation. This is how you find the standard matrix of your linear transformation. What you do? You just apply your linear transformation to the basis vectors. What is the base vector? E1. And whatever answer you get, write it into column. T of E2, write it into column. T of En, write it into column. This is your matrix of linear transformation. And once you got the matrix, now the things become very easy. You get a vector. Okay, I give you a vector in Rn and I ask you, okay, give me a vector in Rn. What do? You just multiply with this matrix. You don't do anything, okay, put the value here, then do this thing. Just multiply with this matrix. So this standard matrix of linear transformation will make your life easy. And this is how you find it. I think this was your question a few months back. So we can find this thing. So I think let us do an example. We are taking the same example. So let me do it here. So I take V in R2. This is my V in R2. And I am applying some sort of linear transformation that takes R2 and gives me output in R2. And then how do I define it? What are the components of my vector? V1, V2. First I wrote the components to be x and y. Doesn't make any difference. And what I get? V1 minus V2 and V1 plus V2. I asked you what is the matrix of this linear transformation. This is my question. I give you a linear transformation. It must be linear transformation. If it is not linear transformation, you cannot convert it into matrix. Because we know very well matrices are linear transformations. If you have a transformation which is not linear, how can you convert it to a matrix? It's not possible. Okay, so let us do it. It's very easy. First thing is, let us check something. What is the linear transformation of 2, 3? You just put here. What is the first component? 2. Second component 3. Put here. 2 minus 3. 2 plus 3. Okay. Keep it here. Leave this thing. Let us find the matrix. How can you find the matrix? What is your standard basis in R1? In R2? Find T of E1. It means apply linear transformation on this one. What do? You pick these and put here. What it becomes? 1 minus 0, 1, 1 plus 0, 1. So, then what is the matrix? T of E1, T of E2 in column form. What is T of E1? 1, 1. T of E1 is 1, 1. Now find T of E2. What is E2? 0, 1. Put it here. 0 minus 1 and 1. Put it in column minus 1, 1. So this